Welcome to Brain Vision.
Hi everyone. What we're looking at today is a problem with thermodynamics and heat transfer. So what we're given is we have a 3-foot cubed rigid tank that's at a temperature of 300 degrees Fahrenheit and is filled with saturated water vapor. We have a supply line that is connected to this tank, which is operating at 200 psi at 400 degrees Fahrenheit, and that's shown here. And what we have is the valve is closed and then the valve is opened. So we know that the tank is exchanging heat with its surrounding, so that the tank is going to stay at 300 degrees Fahrenheit, and the valve is going to close when 1/2 of the volume in the tank is liquid. So what we're asked to find is the pressure of the tank at the end when the valve closes, the amount of steam in the tank, and the heat transfer that occurs. And what we're going to do is we're going to assume that the kinetic energy and potential energy changes are negligible and that there's no work done. So what we're going to do first is define our system, and what we're going to do is define the tank as our system. So our energy balance is going to look like this. Just a simple definition is going to be the energy in minus the energy out is equal to the change in energy of the system. And we're just going to plug in for our variables here, and we're going to say that the initial mass times the enthalpy coming from the line minus the heat that is leaving to the environment is equal to m2u2 minus m1u1. Now the subscripts 2 and 1 are simply our final and initial states. So the mass balance could also be defined as the initial mass minus the mass that leaves is equal to the change in the mass of the system. And we know that initial mass is going to be equal to the mass at the end minus the mass at the beginning. So we can also say that the final pressure in the tank, so P final, which is going to be P2, is going to be equal to the saturation pressure at 300 degrees F. So from the steam table, that is table A4, A-4E, at temperature T1 is equal to T2. Remember, the temperature of the tank is staying at 300 degrees Fahrenheit. The pressure is going to be equal to 67.028 psia. So that is going to be our final pressure. So that's going to be P final. So that's one part of our answer. Next, remember, we're asked to solve for the amount of steam that has entered the tank. So at T1 is equal to 300 degrees Fahrenheit. Remember, we have just saturated steam. So from that same table, A-4E, at T1 equals 300 Fahrenheit, we can find that the specific volume at 1 is going to be equal to specific volume G, subscript G, which is 6.4663 feet cubed per pound mass. Similarly, we can also get our specific energy. U1 is equal to the UG, equal to UG, which is going to be equal to 1099.8 BTU per pound mass. And our specific volume final is going to be equal to 0.01745 feet cubed per pound mass. And likewise, our specific energy at 2 will be 269.51 BTU per pound mass. So also what we can do is, from our steam table, we're going to look at the line quantities. And the steam table A-6E, we'll find that the pressure of the line, we know the pressure of the line is 200 psi, A, and TL is equal, the temperature is equal to 400 degrees Fahrenheit. We'll find that our enthalpy of the line is 1,210.9 BTU per pound mass. Now, we know that the initial mass of the system can be defined using the definition of specific volume, and saying that specific volume is simply V over M1. Now recall that we have volume and we also have this quantity V, specific volume at 1. So rearranging this equation, we can see that the mass of 1 is simply the volume divided by V1. Now plugging in, we know that V is 3 feet cubed, and specific volume of V1 is 6.4663 feet cubed per pound mass. Now plugging those quantity in, we get that the initial mass is equal to 0.464 pound mass. Now the final mass in the tank can be defined with the following expression. It's going to be the mass of 2 is equal to the total volume over the specific volume plus the total volume plus the specific volume, G. Now remember that the tank or the valve is going to close when one half of the mass in the tank is liquid and the other half is some kind of vapor. So that's why we can split this up into saying that VF and VG are both equal to 1.5, because VF plus VG has to equal 3. And we have that condition where the valve is going to close when half the volume of the tank is liquid. So what we can say is we know that this is 1.5 over some quantity VF plus 1.5 over some quantity VG. Now recall that we actually solved for VF and VG from the table, and VF is 0.1745, and again VG is 6.4663. So what this gives us is a final mass equal to 86.2 pound mass. Now we know the final mass and the initial mass, so we can actually solve simply for the mass that has entered the tank, and that's going to be solved using the expression Mi is equal to M2 minus M1, and this gives us a mass of 85.74 pound mass, and that is the mass that has entered our tank. That's part B. Now remember that part C asks us to solve for the heat transfer, how much heat has left the system. So what we can do now is write down an equation for the internal energy of the system in its final state. So we're just going to call that U2 is going to be equal, total U2, remember this is that big U2, is going to be equal to the mass of F times the specific energy of F plus the mass of the gas times the specific energy of gas. And plugging in for these quantities, which we know, this will be equal to, U2 will be equal to 2,300 or 23,422 BTU. Now the heat transfer can be defined as Q out is equal to MIHL plus M1U1 minus M2U2. Now, plugging in for these quantities, we see that Q out is equal to 80,910 BTU. That's our final answer.